morning, friends. I am here again for my favorite course, that is Aircraft Stability and Control. Today I am in lecture number 61, which is question and answer session, and this belongs to the longitudinal static stability, and this is from module 1. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As you know that I have covered whole syllabus from module 1, 2, 3, 4 and 5. Also, we have done the numerical problems, sufficient numbers. I have also completed definition and terminology, and today is my first session for question answer. In this, I have taken some important questions and I am going to answer on these topics. Before I go to the question answer, just I will see that what is the longitudinal static stability. Once I talk about the static stability, it is the ability of any disturbed object. It is the ability of any disturbed objects, or the tendency of any disturbed object is to revert to its equilibrium or trim condition. The keyword here is tendency. Here we are talking about the static stability. We are not concerned how much time it will take to come to the equilibrium or the trim condition. We are just thinking about whether it has the tendency of coming to its equilibrium or its original position where it was before the disturbance. Then we can say that aircraft is static stable. Once we talk about the longitudinal case, the longitudinal is the motion with respect to the y-axis. If I talk about the y-axis, so if this is the aircraft, so if nose is going up and down, so this is the y-axis here, and with respect to this is the aircraft and this is the y-axis. So if it is moving like this, pitch up or pitch down, we can say that aircraft is in longitudinal motion. In longitudinal motion, we have the x direction motion, either forward or the rearward, either plunging and the pitching upward in the jet plane, and the motion of the rotation in a jet plane with respect to the y-axis. If we have like this motion, we can say that this is the longitudinal motion of the aircraft. So here I am going to discuss about this following topics to be covered in this lecture. In this class, questions related to the longitudinal static stability will be discussed, and I have just now told you, once we talk about the longitudinal means if aircraft is moving forward or the rearwards, like helicopter can move rearward also. If it is going up or down, this is called the plunging motion, or this. And this pitching up or pitching down, this is with respect to this black, it is a y-axis. So it is happening with lateral axis, with respect to the lateral axis. So we are, in this class, we are going to discuss about these topics. Now I am going to discuss about state the condition for longitudinal static stability. Okay, so in this, if you can see here that what are the conditions that has to be met to have aircraft longitudinal static stability. And you know that to have all the real aircrafts, when they are flying, they are in the dynamic condition, not in the static. But to have the dynamic stability, we should also have the longitudinal static stability. These all have to be met. So here I am static longitudinal stability or instability in an airplane is dependent upon the three factors. They are the location of the wing with respect to the center of gravity. So the two things are very much important. First thing is the location of the wing or the location of the aerodynamic center of the wing with respect to the center of gravity of the aircraft. Then location of the horizontal tail surface, which is fitted at the extreme aft position with respect to the center of gravity, and the area or size of the tail surfaces. So these are the parameters and which we can. So what is the meaning here? Just I want to the location of the wing with respect to the center of gravity. So the condition, there are the two conditions which I am going to discuss. Before that, I will just see here that this is the wing and this is the tail here. This is the tail and this is the wing. This is here, assume this is the center of gravity, CG of the aircraft. So this is the AC of the tail. This is always represented by the LT. And from here, AC is the AC of the wing. I am writing ACW. And here it is a AC of the tail. So from here to here, you can write as a LW. This is the horizontal distance and I am writing as a LW. So the wing will produce lift. So this wing will try to make nose up. This is called the positive CM. But here the lift is produced like this LT, and this LT into this LT minus CMT will be produced by this tail. So there are two criteria which is to be met. So the location of the wing with respect to the center of gravity. If the AC of the wing is ahead of the center of gravity of the aircraft, wing will produce a positive CM which is unstable or which gives the instability. Just you can see here, this is. So wing will give, most of the wing, their aerodynamic center is ahead of the center of gravity. So the contribution of the wing will always be unstable. So the aircraft will have nose up. So just I will show you here. If aircraft is flying and you don't have the tail, so the aerodynamic center of this wing is ahead to the center of gravity. So this wing will give a lift upward and lift into this distance LW. LW, lift produced by the wing LW into distance, this horizontal distance LW, small LW, capital LW into a small LW will give a moment which will try to make nose up. Nose up is a CM positive, and CM positive means it is a unstable case. So how we can make this nose down? So we need a force, we need another surface which is placed very far away from the center of gravity, maximum aft. So this small aerodynamic surface or aerofoil, and this will make the lift upward. So this LT into a small LT will make it down. So that always we are designing the aircraft in such a way that this LT will try to make the aircraft little minus CM, or it is nose down. If like this, then we can say that aircraft is statically longitudinal stable. Okay, so here we have the two conditions. You can see here this diagram here. The aircraft is flying in this at, these are the alpha angle of attack, and if you increase the positive angle as you are increasing up to the, okay, this is the trim condition, and if you go beyond this trim and you increase the angle of attack this much, it will go nose down like this as shown here, and here it will go nose up. So before the trim, if you increase the angle of attack, it will go up, and after the trim, if you increase the angle of attack, it will go down. Okay, so here we have two conditions. First is Cm naught should be greater than 0 or it should be positive. And second condition, Cm alpha should be less than 0 or negative. Or the Cm naught 0 means the coefficient of moment at 0 degree angle of attack. This is the 0 degree angle of attack, and here you can see here to here is Cm naught, and this is greater than 0 or positive. This is required because if this is the positive, we can get the trim condition at positive angle of attack. Then only aircraft will be able to fly. And if you don't make this Cm naught positive, then it will be like this. So here you won't get a positive angle of attack. So that is why first condition we have to meet that Cm naught should be greater than 0, which is shown here. This is the Cm naught. And this plot, if you see the slope of this is Cm alpha and it is a negative. Means as you increase the angle of attack, slope is going down. So here dCm by d alpha is less than 0 or negative. So these are the two conditions which we should try to meet to have the longitudinal static stability. We can see here that three cases are here. First case here A, B, then C and D. So if it is here A case, as you slope is reducing, it is B, then it has come to the D. It is stable. Up to here it is stable, and as you increase the positive, here it is a positive. Cm alpha is positive. In this Cm alpha is negative. In this Cm alpha is negative, and here Cm alpha is equal to 0. Straight line. If you get the straight line, we will get the aircraft neutral stable. So up to here, from here to here, it is a stable, and from here to here, as you go upward, aircraft will become unstable because Cm alpha is positive, and here Cm alpha is negative. If we are able to make this condition, these are the two conditions which we have to meet to have the aircraft statically stable. Now I am describe the horizontal tail volume ratio and its significance. So you know that horizontal tail. What is the horizontal tail? Just I will show you here. You know that this is the fuselage, this is the vertical tail, these are the horizontal tail, and these are the wings. So this horizontal tail will have some volume. The volume of this plus volume of the left and the right. So area into this distance. Area of the horizontal tail, it means the span of the horizontal tail into the chord, that is the area, and this area into multiplied by the distance of aerodynamic center of the tail to the center of gravity. It is called LT. So if you multiply this, it is called the horizontal tail volume. And if you divide this horizontal tail, the volume of horizontal tail to the volume of the wing, then we can say that it is a horizontal tail volume ratio, and it is called VH. Okay, so I'm going to, so horizontal tail volume coefficient or VH looks like this. VH is equal to ST LT divided by SW and C, where S is actually this ST is a vertical tail area, LT is a distance from the horizontal tail aerodynamic center to the aircraft, CG, SW is a wing area, and C is equal to mean aerodynamic chord. The table below accepts some tail volume data given from the table. Okay, so just I am explaining here. What is this tail volume ratio? So these are the wing, this is the tail. So if you see, this is the here, and if you see, this is the here. You can make like this. Okay, so here, this is the chord of the wing, mean aerodynamic chord. I am writing as a C, and from here to here, This is the CG, this is the AC of the wing, and this is the AC of the tail. This is the tail, and this is the wing. So the area of this, what is the area? SW. SW into chord is equal to C. So you got, this is the volume of wing. Now volume of the tail is what? It is area ST into LT. LT is what? Here. From here to here. This is the LT. Okay, so this volume ratio is equal to ST LT divided by S into C bar. So this is called the tail volume ratio, and it is very much important because the tail volume ratio gives the longitudinal static stability of the aircraft. Okay, this value of ST, LT, if you vary this thing, your VH will vary, and this VH will make the Cm naught greater than 0 and Cm alpha less than 0. These two parameters can be achieved with the help of the tail volume ratio. So this is the important parameters to maintain that aircraft is longitudinally static stable. Now I want to discuss about downwash and its effect on the aircraft. So what is the downwash? So first I want just explain you what is the downwash. You see here, this is the aircraft. If the wind is coming from this direction, due to this slope, and here also in the wing, it is upward due to the camber, air will flow like this and it will go downwards. It will start from here and it will start downward. This downward is called the downwash. And this downwash will affect the actual angle of attack experienced by the horizontal tail. The actual angle of attack experienced by the tail will be little reduced than the free stream velocity which the wings are facing angle of attack. Assume that wing angle of attack is 5 degree. Here you may get 4.5 degree. Less than that. Always, because wind is going like this. Due to the circulation which is taking place due to vortices formed on the aircraft wing and the fuselage, these vortices will hit the horizontal tail as well as the vertical fin. But we are in this time only considering the horizontal tail. In horizontal tail, you will get the different angle of attack due to this circulation. Just I want to show here again by the small diagram. So these are the wing, and this is the tail. Okay, here is the CG. Here is the AC of the wing. This is the AC of the tail. This is the tail, and this is the wing. Okay, so what happened? Just I am taking only wing and the tail. I am not considering the fuselage part. So if you see here, the flow is going from here and it starts circulating. You just see here. It will try to go down, and this downward will hit here with a little lesser angle. Assume that here your angle of attack is alpha. Okay, so here this is alpha W I am writing here. So here what will be the angle of attack? If the circulation is not taking, this angle and this angle will be same. But here you will get alpha T, this angle. This is alpha T. And this alpha T, what will happen? Here the velocity is V, and here I am writing velocity is V prime. So this alpha prime will be less than the alpha W. Okay, and here this is the alpha W minus d epsilon by d alpha. This much variation. And what is this? If I make this is the V of the wing. So here this will be like this. This is the V prime. Okay, here. So this is called epsilon and this is called the downwash angle. This epsilon is what? Downwash angle, and this downwash angle will definitely affect the LT lift produced by the tail, and this is little lesser than the what it's supposed to be in the actual condition, and this is happening due to the vertices here behind the wing. Lot of vertices will be formed and these vertices will develop the downwash, and downwash effect is to reduce tail angle of attack. Okay, that is the specialty of this downwash, and its effect will be the effectiveness of the tail will be reduced due to the downwash of the aircraft. So we need little extra tail volume ratio so that the size of the horizontal tail will be little increase. The weight of the aircraft is going to increase by the effect of the downwash. Next is contribution of fuselage on longitudinal stability. Okay, so you know what is the fuselage? Fuselage is the main component of the aircraft where all the materials, all the passengers, all the equipments are stored. So here this you can see in this Boeing aircraft of Indian Airlines. I have taken a model. So here this part here is your fuselage. So here the pilots are sitting, it is the cockpit, and from here to here the passengers are there. Below this is the fuel. In this wings also there are fuel. Lot of equipments, avionics equipments are also stored here in this part of this aircraft. So fuselage is one of the very important component. Without this, no use of the aircraft. But how it will affect the longitudinal static stability, that we are going to understand that which part. So if you can see here, this is the nose, this is the main body, and this is called the bow tail. This part from here to here, and if you see from here to here, it is like a cylinder. But here it is a cone, and here it is a reverse cone. You can say it is called the bow tail. So what is the effect of this type of body if aircraft is having the fuselage? So what the fuselage will do for the longitudinal static stability? So just I am explaining here. This we can divide into three parts. This is the first part of I have shown you. This is the second part, which is very, very long. I am just making a dotted line here. And this is third part, which is called the bow tail. And bow tail is where the last part where vertical and horizontal tails are fitted. Okay. So I am just discussing what is the effect of these parts. So I am showing this thing. Okay, so this is the nose. This is the main body of the fuselage. And this is called bow tail. Okay. So here if you see, here is your tail, and here is approximately your wing. Here is your pilot. Okay. Here is the pilot. So if you see that aircraft is flying, and this is the angle of attack, alpha. So what this nose part will do? This you can see here. If you see that this is the point, so here the lift will be generated in this direction, and here is the CG. So this lift of the nose, I am writing ln, and this is from here xn. So this will generate a moment in this direction. I am writing cm by nose. So the direction is clockwise. If you see here also alpha, but it will not affect because it is passing from the center of gravity and it is in the same as a cylinder as is shown. So here it will give cm0. But here what will happen? Again, if it is alpha here, so here it will again, and this will produce in the same clockwise direction. So this effect of this will be, this lift will be in this direction, not in this, just sorry. This lift will be generated in this direction. So this is called LB. LB into this XB. XB. So this moment by CMB will be LB into XB. And direction is what? Again clockwise. So here clockwise, nose is also clockwise, tail is also clockwise. So net moment CM by fuselage will be CM of nose plus CM of body plus CM of tail. Okay? So main body. So here this and this both are the positive. Plus 0 plus. So here you will get the plus moment in this clockwise direction, and this will give unstable aircraft. So the effect of fuselage will be, aircraft will be unstable. So the contribution of the fuselage is to give a unstable longitudinal static stability. So that is the specialty of this contribution of the fuselage. Now what is the neutral point? What is the neutral point? You know that I have shown in the question 1 that if you make the CM versus alpha plot, and if you see here 1, 2, 3, 4 and 5. So here if you see in this plot, dCm by d alpha is equal to 0. No slope. So this condition, when the aircraft do not have any Cm by alpha slope, this is called the neutral position or neutral stable, and this will happen when XCG, the center of gravity of the aircraft, is overlapping with the aerodynamic center. So this neutral point is related with relation with neutral point aerodynamic center plus this center of gravity location of the aircraft. So just what is the neutral point? The neutral point is the position of the center of mass where the aircraft would be neutrally stable. If you put your center of mass behind, after of this point, you will get an unstable aircraft that will increase turn with an maneuver, any maneuver the pilot takes place. This you can see here. This is the diagram here. It is in the equilibrium, and just you can see here. So this is the condition. Your aircraft is here, and this is the trim. This is the case 1 here. This is the case 1. As you increase the angle of attack here, in this what happens? The CG is over the AC of the aircraft. If like this, then what will happen? Aircraft will be going straight in the same position. You see here, it is disturbed, but you increase the angle of attack, aircraft will maintain the same position up to unlimited time. No movement of airplane holds the disturbed condition. It means it is not coming down or it is not going up. It will maintain the same condition here, 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 and aircraft is like this position, the point when the center of gravity of the aircraft is reaching to the aerodynamic center of the wing, then this aircraft has become the neutral stable, and that point is called the neutral point. So it is that fictitious point of aerodynamic center where center of gravity and aerodynamic center are in the same position. In this case, if you disturb the aircraft, it will maintain the same attitude or the same location or same angle of attack. It cannot come back to its equilibrium position, but it will maintain in the same. However, it will not increase also. It will not diverge and it will not converge, and it will maintain in the same condition. This we can see here that aerodynamic center of the horizontal tail behind the leading edge of the wing mean aerodynamic chord, it is 0. If the CG were located at the position, the vehicle would be considered as a neutrally stable. So if the distance between aerodynamic center and the CG both are 0, it means, just I am drawing here, this is the nose, here is the CG, and this is the AC. If this CG is moving like this, and this CG has come to here and on top of this, so this is called now the neutral point. This aerodynamic center, when CG and AC both are in the same point, then this is called the neutral point. Somewhere it is NP, somewhere it is N0 also. It is described, and we are putting the bar to have the non-dimensional numbers. Effect of the propeller on static stability. This we are going to discuss next. So till now we have not seen that how the engine or the propellers are affecting on the static stability. So the effect of the propeller can be seen with different configuration. We have the puller propellers and we have the pusher propellers. So if the propellers are fitted ahead, just I am showing here, this is the aircraft. If I am putting this is the fuselage reference line, it is called FRL. Here is the center of gravity. Here, as you can see, this is the wing, and here is the tail. Okay, so if I am putting my propeller here, it is a puller type. It is throwing the wind like this, and aircraft will go in this direction. So this is the propeller. Assume that angle of attack is alpha. Okay, here I am exaggerating the more. So what will happen? If everything is same, due to the rotation of this propeller, one force will be acting in this direction. Another force, due to this, it will act vertically like this. I will write as a thrust vertical and thrust horizontal. So you can calculate now. It will affect the coefficient of moment. However, it is fitted at this FRL line itself. So this TV thrust produced in a vertical direction due to this rotation of a centrifugal force will be generated, and some part of this thing will be in the vertical direction. This force into this distance from here to CG, just I am writing X thrust XT. So this into XT. This is what is the direction of this? This will be clockwise like this. So this moment will generate a moment Cm in this direction. So this Cm will be a positive or clockwise. So you know that if the Cm is positive, then it is a unstable. Okay, so the propeller which are used, they are making the aircraft unstable if it is a pusher. What will happen if I am putting a pusher one here? I am putting one propeller here. So what will happen? This will also generate like this into this. So if it is a puller, then it is give the Cm alpha negative. This negative makes the aircraft stable. So if you want to make your aircraft stable, try to make or fix your propeller behind. If you are putting the behind, it is stable, and if you are putting at the nose, the propeller here, and it is rotating, it is pushing like this, it will give nose up. But if you are putting here, it will go nose down. So the puller is giving stable, the behind one, and the at the nose it is giving the unstable or the positive Cm, and behind one is gives the negative Cm. Now effect of the CG on static stability. Effect of CG on static stability. We know that the CG is very, very important. This is the CG, and here I am writing the neutral point NO. And you know that if I draw the plot, Cm versus Cl or alpha, whatever is there. This is the CG location 1, CG location 2, CG location 3. CG1, CG2 and CG3, and this is the neutral point. So if I draw the plot of 1, this is the Cm naught, and this will go, and this is the CG1. If I draw the next plot for CG2, it will be CG2. If I draw for the plot 3, it will be CG3. Okay, but if I draw the plot when CG is above the neutral point, then the plot will be parallel to the horizontal, this. So this is called neutral point. When the CG, so there will not be any slope, and the dCm by dCl is equal to 0. This point, so the effect of CG, as the CG is moving towards the neutral point, the stability of the aircraft reduces as the CG moves towards the neutral point. And this is the limitation. This is the limitation of the CG, the aft limitation. Aft limitation of CG is up to neutral point. Neutral point. But how much you can make the forward? You are here. But how much you can make? You can make here, here or here. Up to where you can make? The forward limitation, the forward limitation of the CG is depend upon the maximum elevator deflection available. Okay, so forward is depend upon the elevator, and the behind rearward depend upon the neutral point, because after this if you go, aircraft will be unstable. Okay, so if your CG is moving here, aircraft will be unstable. If it is in this side, it will be stable, but high stable we don't want, because it needs more elevator and it will be restricted by some point depend upon the elevator deflection. So that we have to keep in mind. Most forward and aft CG location to maintain static stability. Okay, I think this I have already explained you just now. So most forward, how much? So this is the neutral point. This is the CG. So most forward, how much you can go? This is the nose. This is the nose of the aircraft. Nose of aircraft, and this is the, here it is a tail. So this is the neutral point. So how much forward it can go? The forward it can go, it is depend upon the elevator, maximum elevator deflection allowed. Every aircraft is given nearly 25 degree to 30 degree plus minus is given. So this is the limitation for the forward. But for the rearward, how much? Rearward is depend upon the neutral point. So neutral point NO is the last point for CG to move aft of the aircraft. Beyond this, aircraft will be unstable. Okay, so these two parameters we have to consider very well. What is canard? How this affect the aircraft stability? So, what is the canard? Canard, if you take this aircraft, in this tail, if you remove this tail and fix at the ahead of the wing, this one, like this. So, this black, this remote, it will become your aircraft. Canard. So, what is the effect of the canard which we are going to discuss? A canard is an arrangement wherein a small forewing or foreplane is placed forward of the main wing. Okay, just now I have shown. So, this is the small wing I have put forward of the main wing of a fixed aircraft or a weapon. This is also used in missiles and all. So, it is called weapon. A canard is used for several reasons, such as increasing lifting force. It will increase the lift force. However, the horizontal tail will act downward. So it is not useful. But if you are putting the canard or ahead, the wing, a small wing ahead of the main wing, the lifting force will be in the same direction as the lift of the wing, and it will give a positive thing. Okay, so the stability of the aircraft control and flow changes over the main wing. So here this, you can see the difference. Here it is a canard, here a small wing, and this is the wind gust. Here is the CG here. So if the wind gust came, it will increase the lift upward, and here also the lift will be upward. So this L of the wing plus L of the canard will be total lift. But if you fix a tail here, so L of the wing minus L of the tail will be total lift. So your canard will give a better lift efficiency or the better L by D ratio, and also it will give better control as it is in the free stream. The whatever control you apply, it will not be disturbed. As if you are putting behind, your wing will disturb, a downwash will affect on the wing. But in this case, it will not going to affect. Now, trim tab and the balance tab. What is the trim tab and the balance tab? You know that when the aircraft is flying, pilot has to apply the control. It may be rudder, elevator, aileron. So, if he is applying and if trim tab is not there, elevator is deflected, he has to hold in that position. How much time it will hold? One hand will be busy only holding. If you are applying the rudder, your foot will be also applying. So all the hands, your feet always will be busy. This is not good. pilot should fix the attitude or the direction and the height and all the things, and he should leave the free hand. He should have the free hand, so he or she can observe the location or the condition here and there. In this way, the pilot can do a better way and it can perform nicely. So we need the trim tab and balance tab. So here, trim tabs are small flight control surfaces that are attached to the trailing edge of a larger primary control surfaces such as an elevator or rudder. The trim tab is used to trim or counteract the aerodynamic force on the control surfaces and thus stabilize the aircraft in the axis of rotation associated with the primary control. Trim tabs can be either flight adjustable or fixed. So this can be fixed also. So just I am showing you here. We have the three controls. These are the ailerons. Okay. This is the aileron. This is the rudder. And this is the elevator. So here, this is your whole aileron of one side, and here also you have aileron of, and these are the flaps. So you know that here, this blue color, this is called the trim. This is called the trim tab. What happened once you roll the aircraft? Just I am showing here. Just I am showing the first. I am showing the pitching. What happened for pitching? If you want to pitch up, then here these are the elevator. Elevator has to go up. If the elevator will go up, lift will be in this direction. Nose will go up like this. Nose will be up. So if you want nose at 5 degree, just assume it is a 5 degree and pilot is holding like this. He cannot hold. So how? So in this, just I am showing you, this is the tail, this is the elevator, and here is a small tab. So if you see, if you deflect, I am deflecting elevator upward like this. So I have to deflect this tab. This is called the tab, and this is called elevator, and this is the horizontal tail. So you know that you have turned. So it will, if you are making up, lift will be in this direction. But if you make this thing, this will be upward. So this moment and this moment will be balanced, and aircraft will maintain the same 5 degree. 5 degree what the pilot has given, and after that he will select a trimmer, and from there it will adjust in such a way that aircraft will maintain same attitude. He need not to deflect, or he need not to hold the control stick, and his hand-free flight it can be done. The same way it can be performed by the aileron also and the rudder also. So rudders are operated by the help of foot, and left foot or the right foot, pilot has to press it. So if you are pressing here towards this side, then your trim will come towards this, opposite to the deflection of the main control. Trim will be always deflected opposite to the main control of the aircraft, so that the pilot will have a free hand in all these three axes, that is the longitudinal axis, lateral axis, and the directional axis. So if these rudders are used for the directional, so if you want like this, it will deflect the rudder in this direction, the trim tab will go opposite to the direction of the deflection of the main control. So these three things we can understand by this. Now, what is the balance tab? You know that trim tab is, but balance tab is by itself, it is a balancing, and we have some different types of balance so that these tabs will balance the aircraft. So balance tabs moves in the opposite direction of the flight control trailing edge, providing a force that helps the flight control move. So it is used to help the pilot. He or she should not apply more forces. These will generate its own forces and it will counter the action of the flight control. This you can see here. Aileron horn. It is called the aileron horns. This you can see here. These ailerons, these are deflected upward. So this part has come downward. Okay. So if you deflect this, the force here will be generated in this direction. But if you make like this, force will be in this direction. This force and this force will be balanced. So it is initially during design only it is prepared. So these type of things are called the balance tabs, and they are going, the nose part will go opposite to the tail part and your moment will be balanced. Next you can see it is for the aileron. Now this is for the rudder. Okay, so this you can see here that it is for the rudder horn. So you can see this is the rudder, and this is the vertical tail here, and here is the blue color is the rudder, and this green it is called the rudder horn. So if the rudder is, just I will show you here. If you move the rudder like this, in this direction, this horn will go in this direction, opposite. Okay, from here to here, it will go opposite. So if the force will act in this direction, but in this force will act in this direction. So force of this horn FH and force of rudder both will be balanced. So pilot need not to apply the force continuously. Okay, so once it will deflect and it will adjust this balance tab, and it will give a hand-free or free-hand aircraft. The pilot need not to do any foot motion and it will be balanced. Next question is, during a flight, due to passenger movement, CG of the airplane moves away from neutral point. Due to this, the elevator angle required to trim the airplane will be increased or decreased. Okay, so what is the question? During a flight, due to the passenger movement, CG of the airplane moves away from the neutral point. Due to this, the elevator angle required to trim the airplane will be. Okay, so just I am drawing first. This is the delta E and this is the CL. So initially it is like this. Assume this is the delta E 0 and here is your location of the CG. Okay, so this is the CG at the trim condition. Now if you move forward, so this is the nose and this is the tail. If you move from here to here, then what will happen? So if you draw from here to here, then for this you need this positive. Delta E required is positive. If you are moving forward, it is moving in this direction, So what you have to do? This is your tail, and this is should go down. This is called delta alpha E positive. So if your CG is moving ahead, then a positive deflection of elevator is required. And how much positive and how much ahead you can go, this depend upon the maximum available delta E. It is plus minus. It can go as if it is going behind, then it can go upward like this. Okay, so it is a minus delta E and this is the plus delta E. So angle required to trim the airplane, elevator angle required to trim the airplane will increase. So you have to increase the angle of attack as I have shown here. Initially it was here 0, but now it is increased to some plus delta E going downwards. So it is increasing the angle of attack. Now next question. For an airplane flying at an altitude with trim condition is CL1, velocity is V1 and angle of attack is alpha 1. Now the airplane wants to fly at a new CL2 where CL2 is greater than CL1. What will be the velocity? So at the CL1 velocity is V1. Now the airplane wants to fly with a new CL2 where CL2 is greater than CL1. Okay, so just I am making here. So this is the trim, this is the CL. You assume it is a CM. So this is the CL1. Now it is a CL2 and CL2 is greater than the CL1. So if you want to fly in this, what will be the velocity? V2. And here is V1, alpha 1 and CL1. CL1, V1, alpha 1, CL2, V2, alpha is constant. So what will be the velocity? It will be more or less than V1. So that we are going to discuss. So we know that CL1 is equal to 2W by rho V1, and now CL2 is equal to 2W by rho V2 square. Actually 2W by S is supposed to be S. Okay, but it is. So now CL2 is equal to CL1 V1 square by V2 square. Okay, because these things are common. So CL2 is equal to what? CL1 divided by V1 square by V2 square. But we know that CL2 is greater than CL1. So it proves that V2 by V1 here, V2 by V1 is equal to CL1 by CL2 under root. So V2 by V1 is equal to CL1 by CL2 under root. So here, hence the V2 will be less than V1. This is the answer. So this here V2, if suppose it is 100 meter per second, the V2 may be 80 meter per second. So if you want a high CL2, your speed has to decrease. Other conditions if all are same. Okay, so that is the, hence V2 is less than V1 and that is the result. Okay, so hope this I will do in the next class. Okay, so I have completed this my question and answers session and hope this will be very useful. In next class, I will be handling the lateral and directional static stability. And please be tuned. I will be taking some more questions and I will be discussing in detail. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.